Okay, let's go over a combination circuit problem. Combination circuit analysis, a little bit more challenging. It makes sure you guarantee you know everything. So our objectives are to review series and parallel circuits through a combination circuit, and we're going to analyze combination circuits, and then we'll go back over Kirchhoff's laws and VERP tables to solve it. So a combination circuit is one that's composed of series and parallel parts. In the real world, oftentimes that's how we wire things. Part of it will be in series and parts of it are in parallel. It would look like that. There's a battery and you have two complete loops. Notice how the top resistor is going to be in series since all the current has to go through that part, and then the other two resistors are in parallel. This is a simple one. Obviously they can get more complicated looking. Now I total, it has to equal I1 plus I2. That's Kirchhoff's current law, saying that everything that goes into a junction has to come out of that junction. So I total is equal to I1 plus I2. Now V total, and I total would also be on any single line of that circuit. So the current that goes through all of those resistors comes out all those resistors, but it's lost all its energy. It's converted that energy into something else in the real world. Now V total, which is what's coming out of the battery, has to equal V in the series part. Now when it goes through that top resistor is going to use up a good chunk of the energy, and a good chunk of that voltage is going to be used up before it ever gets to the parallel part. So V total is going to be V what's ever used up in the series plus V what's ever used up in the parallel part. So although these two parallel resistors are going to have the same voltage drop, they will not be equal to what the battery is, because that first resistor took some of it away. I can put that resistor on the bottom. It's still going to function the same way. It's going to take up some of that voltage. Remember, the wires are full of electrons, so as soon as I start moving one, instantly everything in the circuit affects everything else. Okay, let's try a sample problem. So sample 1, we have a 60 volt battery, a 2 ohm resistor, and then we have two parallel branches. One parallel branch is 6 ohms. The other parallel branch has a 4 ohm and a 2 ohm resistor. So first thing we have to do is solve for our total. Now the first thing I want to look for is series circuits on a parallel branch. The right hand branch has a 4 and a 2. I have to combine those first. Then a parallel branch is then a long series circuit. So step 1, the first thing I have to do is combine those two. So 4 plus 2 is equal to 6. Now it helps to be able to redraw the circuit at this point in time. A 60 volt battery, a 2 ohm resistor on the top, a 6 ohm and a 6 ohm. I've put the 4 and the 2 together. Now later on in the VERP table we will go through and solve them separately, but right now we've put them together. Now next thing I want to do is simplify the parallel part. That's step 2. 1 over R parallel is equal to 1 over 6 plus 1 over 6. Well, 1 over R parallel is equal to 2 over 6, so R parallel is equal to 3 ohms. At this point in time I would redraw it. And you have a 60 volt battery, you have a 2 ohm resistor, and I've replaced that entire parallel part with a single 3 ohm resistor. So therefore now what I have is a long series circuit. I simply add them up. In this case it's going to be 5 ohms. So that's the resistance total for the entire circuit. Okay, now let's draw a VERP table and we'll put in the things we know. We know that the values of the resistors, so we can put those in. We know the resistance total. We know the voltage total. We also know the I total, and I'll show you how to calculate that. Now I total is going to equal V total over R total. Well, remember, if you know two things in a line, you know everything else. 60 divided by 5 is 12 amps. So we know the total current is 12 amps. What that means is I have 12 amps going through that top resistor. I also have 12 amps going through that bottom wire. So that's important to know to be able to solve it. Okay, let's go through and calculate some other stuff. Now, I want to calculate V1 because V1 is going to be taken away from the 60 before we ever get to the parallel parts. Well, V1 is equal to I1 times R1. I think using the subscripts helps you keep track of everything. So don't cut corners and not write them. It's just easier to write them and include it. So therefore, well, we know that I1 is 12 amps. We know that R1 is 2 ohms. 12 amps times 2 ohms is 24 volts. So then I can put that in the VERP table. What that means is I started with 60 volts. Through that first resistor, I use up 24 of the volts. Now let's continue on with it. We'll recopy the VERP table down. You still have it. And we know that that's 12 amps and that's 24 volts. I'm going to leave that up there to help myself. And now what I want to do is calculate the rest of them. So let's calculate V2. Well, V2 is going to be V total minus the 24 volts that R1 used. So it's 36 volts. So R2, the voltage through R2, is 36 volts. So I can put that in my table. Now, if I know two things on a row, I know everything else. So I2 is going to be equal to V2 over R2. 36 volts divided by 6 ohms is 6 amps. So therefore I know that. Now if 6 amps goes through R2, well, if you remember, R2 and R3 and R4 combined both were 6 ohm resistors, so it's going to split equally. So I know that I total is going to equal whatever goes through I2 plus whatever goes through I3 and I4. So I know I had 12 amps. I know I2 is 6 amps, so therefore I3 and I4 have to also get 6 amps. Remember, if it's going too fast, you can go back, you can rewind it, you can stop it, you can pause it, and catch up until it sinks in. So now I want to go through and calculate V3. Well, V3 is going to be I3 times R3, and I have both of those values. 6 amps times 4 ohms, 24 volts. Now the same thing for V4. V4 is going to equal I4 times R4, which is 2 ohms times 6 amps, which is equal to 12 volts. Now you can calculate power. It's simply V times I. I didn't do it because I know you can do it. Now let me show you a way to check these problems, and we're going to check these problems using Kirchhoff's loop rule. Now Kirchhoff's loop rule says everything around a closed loop, all of the voltage must be used up. So delta V has to equal 0. So if I have 60 volts coming out of the battery, in that particular loop I have to use up 60 volts. So for my first loop, which is the one I've shown, I have 60 volts minus the 24 volts used by the top resistor minus the 36 volts used by R2. 60 minus 24 minus 36 is equal to 0. So that one checks. Now we're also going to check the other loop. The second loop is that long big loop. It goes through out of the battery, it goes through R1, it goes through R3, it goes through R4 before it comes back to the battery. Now I know the battery added 60 volts, so I have 60 volts minus 24 volts, that's R1, minus 24 volts, that's R3, minus 12 volts, which is R4. 60 minus 24 minus 24 minus 12 is again equal to 0. Hope this helped. And again, go back through it if it was a little bit sketchy for you.